Okay. Yeah, yeah. When I do these things, I try to think of three audiences in mind, actually. You guys are number one. So you're the first people I'm talking to. All right. And I'd really looking for a lot of really good questions and a lot of help. Uh, Gary, hear us?
Yeah, it's good. It's good.
Okay, you're hearing me all right?
Yeah, beautiful.
I'll just speak loud.
Beautiful.
Okay. What I'm going to be talking about today is something that's called an analog to digital converter. And the analog to digital converter is kind of a device that takes our analog signals across the spectrum and converts them into a computer format so that the computer can deal with and process the signals. This is the key to every modern radio made today. Analog converters can be found in all kinds of things. My PC, your PC is full of these things. They're used for all sorts of purposes. Internet of Things is really strong with A to D converters. It's one of the most important electronic devices out there, and it's one very few people have heard of. So I'm going to do this as an introduction to A to Ds. Okay, Marty, you want to change the slide? Okay, so I'll be talking about a brief history of receiver architectures, because this is where we're going to put them. It occupies a key place in just about every receiver made today. Now, a lot of us like working on all the old equipment and so on, and I have some examples which we'll see. But nobody would build a thing like that today because it couldn't use yeah, yeah. Go back to the agenda, please. Yeah, yeah. Thank you. Okay. So I'll talk about what it does, and we'll talk about some terms that we see in that we all know with bandwidth. Okay. What is the bandwidth of these things? What is sampling? And what's a sampling rate, which is how these things work? Okay. Aliasing, which is an interesting distortion that these things have that a regular radio does not have. Something called the Nyquist frequency. And I have a brief couple of slides on Harry Nyquist, who developed the theory. The stuff is not new. Harry Nyquist did this stuff in 1928. But it took a long time for the industry to come around to recognize how to build the equipment that he had defined and described. Okay, resolution. And that has to do with how we quantize this information to make it compatible with the computer. What's the dynamic range? You know, at the low level, it's noise. You know, all the crap your antenna picks up, all the garbage. All right, that's noise. But then again, that strong broadcast signal, for me, you know, when I was a kid growing up, the strongest signal in the spectrum was channel 21, which was a whopping probably about a mile and a half from where my parents lived at the time. And they had one hell of a powerful signal. And in fact, when I misconfigured my stereo phonograph, I had a magnetic phonograph preamp, I could pick up the sync buzz from channel 21. And the only reason I know it was that they accidentally went off the air and all of a sudden the sync buzz disappeared from my stereo. So go figure. They were running 10 amps at 25 kilovolts into a Klystron amplifier into a gain antenna. So you can imagine how strong that signal was. Yeah. Okay. We're also going to talk about jitter and dither, which are some kind of strange names. Spurious responses, which of course all receivers have. So digital receivers are not immune from this. And we're going to talk about how we build these things to avoid them. We're going to talk about linearity, which is a form of distortion. And like I said, I have a couple of slides on Harry Nyquist. So if you wonder who did this in 1928, I even got a picture. So here we go. Okay, next slide, please. Okay, brief history of receiver architecture. And to this stuff, I owe a lot of gratitude to Ed, WB2EAV, who put together a number of talks for us previously on receiver architectures. So on the left, we have a tuned radio frequency receiver. And the picture is that of an Atwater Kent Model 20, which was a pretty popular machine at the time. It used 501A tubes. It was powered by batteries. It had a Horde type speaker, which I didn't have the room to put on in the picture, but it basically had three independent sets of tuned RF circuits that would tune in a station. And there was really no clear concept of exactly how to tune in a station with this thing. So it was experiment. So lots of guys loved tweaking dials and so on, and this thing admirably fit the bill. But to the average person that just wanted to listen to the radio, it was a PITA. So those things kind of vanished pretty quickly, and by the early 30s, they were gone. Okay, so what happened? A guy named Ed Armstrong, you may have heard of him. He invented the superheterodyne. He invented super regeneration, and he invented FM. Holy crap, that's a lot of stuff. And then David Sarnoff came and robbed him of all that. So, yeah, patent wars. Anyway, so he built a supersonic heterodyne, which of course we call the super heterodyne receiver today. And the reason why he built it that way was filters at the RF side were expensive and you had to twiddle with them, and that was a real pain. So what he did was he figured out at a lower frequency than our RF band, say 455 kilohertz, for example, we could make a nice IF frequency that's easy to amplify, easy to get good selectivity out of. Now, all we have to do is figure out how to change the frequency of all the stations we want to listen to. And that's what he did. So he put a local oscillator that you could tune either 455 kilohertz above or below the station that you wanted to listen to. The IF stage would provide most of the amplification. It would provide the filtering. And all you had to do was have a very simple RF stage to pick up the stations you wanted to hear. And hence we had a super heterodyne. It became extremely popular. It was invented in 1990. Am I there? Okay, good. Okay, so in any event, this stuff was actually invented right after World War I. And in 1924, Sarnoff stole the patents. And here was the first RCA Radiola AR-812. That was the very first super heterodyne receiver made, as far as I can tell, that was actually sold for production use. And people were buying them, became very popular. And super heterodyne just wiped the heck out of super regen, which was twiddly and kind of hard to adjust the detectors and easier to tune than the TRF machines of the day. Okay. And from basically 1924 or so until about the year 2000, most things that were called a radio actually used a super heterodyne, right? And I'm sure most of us have super heterodyne equipment one way or the other. All right, next slide, please. Is it being very slow here? Use the down arrow. Okay. Well, I have it here, but not there. Okay, here we go. Right. Okay. What happened during the 1970s, 80s, and 90s is everybody know nobody was playing with radios anymore except us. People were playing with computers of all kinds, and we went through all kinds of phases very quickly in the typical S curve of what does a computer do. So pressed by the requirements for the need to add the analog spectrum to our computers, we came up with this idea of taking an analog circuit and computerizing it. And in this case, it means using that wonderful word quantum. And no, this is not quantum mechanics or quantum physics. It deals from the word quantize, which means put it in a little box of measurements. Okay, so we could put all our measurements in a simple box. And there was a device made, a semiconductor device made called an analog to digital converter. And what does it do? We take an analog signal and we periodically sample it. That means we feed it a fairly high frequency clock signal. And every time that clock appears on the analog to digital converter, the thing takes a measurement. Okay. And the measurement it takes is how strong is the signal at this particular time. Okay. And it feeds that out into the computer's memory. And it's done. It goes on to the next one. It's up to the computer to figure out what to do with that signal. Okay. So each time we have that sample, okay, and that's called the sampling interval, we're going to measure its amplitude. We're going to quantize that output, and it's going to become a digital bit stream. And once it's safely inside the computer's memory, the software is going to decode that digital bit stream and extract the information from the signal and via software convey it to us in the appropriate format. If it's video, we'll see a picture. If it's sound, we'll hear something. And if it's text, we'll see it. Okay, could be any of those things. All right. So what we have for receivers is the first generation on the top and the second generation on the bottom. The earlier receivers worked within the limitations of analog to digital converters. Like any other semiconductor device, these things went through a huge evolution going quick. Okay, so the first one is called a hybrid, in which we take a circuit that looks surprisingly similar to our superheterodyne circuit. Okay, we go through a filter, a low noise amplifier, another filter, and we go into a mixer. And yes, it's a superheterodyne mixer. There's an LO, there's a sum and difference frequency, goes into a little IF amplifier, goes into a filter, and then that goes into an A to D. Why do we do this? That looks pretty complex, and it is. But we do that because analog to digital converters at the time were ridiculously expensive, and the resolution was pretty poor. So what happened is, by making the frequency that they'd have to work at a lot lower, we could put in a reasonable cost A to D converter. And a lot of rigs use this technology, the so-called hybrid. So it's a true software-defined radio because the software is sitting on the output side decoding the signal, but it's a relatively inexpensive A to D converter. That's neat. That's right. Well, it's after the IF. Right. Okay. Then we have the so-called direct, which we're seeing more and more of today because A to D converters have become faster. They have more resolution. They have less noise. And it actually becomes less costly to avoid a mixer and an oscillator and all the filters and stuff you need. And this stuff can now be put on a chip. So what happens is now we have the antenna feeds an RF gauge, a low noise amp, going into a filter, going directly into the A to D converter. So now there's no intermediate steps, no frequencies to convert, etc. So the A to D converter is actually looking at the RF spectrum as picked up by your antenna and sampling that directly. And that works great. And it gets rid of a lot of problems, but the A to D is a lot more expensive because it has to sample a lot more quickly. So that's the trade-off. What happens, though, is it's all digital technology at that point. So the device is getting cheaper and cheaper as they figure to put more and more of this stuff on the chip. So this has the potential for a lot of cost cutting. Super heterodyne receivers are not especially popular because you can't put all that stuff on the chip. And when you can't put all the stuff on the chip, the price goes up. Just for information, this thing here has a whole bunch of SDRs in it. Your cell phone has 3G, 4G. If it's a newer phone, it probably has 5G technology, and that's at least 3 different radios. It has Wi-Fi at 2.4 gigs and 5 gigs. That's 2 more radios. It may have Wi-Fi at 6 gigs using some of the newer Wi-Fi technology. And it has Bluetooth. And Bluetooth has 7 different modes of operation. So we have how many radios? A dozen? This is in your phone. Just about every phone has this stuff. And by the way, 6G is coming. They're working on it. Okay, next slide, please. Yeah, oh yeah, there's lots of different filters with different functions. We'll talk about that. Okay, so here we have a picture of something that was actually made by AMSAT, and this was from a QST magazine probably about 8 years ago. This is in the 2016 QST magazine. So here we go again. The A to D converter is a circuit that takes an analog signal and measures it. And let me repeat that word, measures it, something the superheterodyne doesn't do. This is actually going to quantize that signal. It's going to convert it to a digital format, and it's going to be extremely precise. And I'll talk about how precise it can get. So it's going to convert a continuous time and continuous amplitude analog signal to a discrete. That means there's steps instead of being smooth. So we think about a staircase. You can have a ramp or a staircase. The digital one is the staircase. The analog is the ramp. Okay. Quantization, which is what we're doing with this thing, is the process of constraining an input from a continuous set of values, such as real numbers, such as some voltage, which is varying from 0 to 1 or whatever the voltage is, typically the stuff picked up by your antenna. And we're going to change that into a discrete set of values of both time and frequency, based on approximating something that if you have a sine wave, it's going to end up looking like a staircase. And I have some slides of that. And the conversion involves quantization of the input. So it introduces a small amount of error, okay, because you can't precisely quantify some. Question, Brian. Oh, yeah. Yes, it does. I'll talk to that. At least I hope I will. So yeah, as I'm going, bother me again. It's good. No, that's something important to know. So thank you. Okay. Yeah, the quantization involves putting the input into a stair step. Okay. So if the step size is small, it sort of doesn't matter. But if the step size is very large, i.e., you run out of bits, or you're really using a very cheap A to D, take your pick. It may have an error that'll affect the quality of the signal or the quality of the sound. And that's something we have to be attention to. You got to make sure that it's going to be accurate enough to do the job that it has to do. Okay, so that's important. So as it's continuously performing its conversion, it's going to be sampling the input, and it requires, as you're doing that, to put some limits on the input. Okay, it's possible to overload an A to D converter. So, once you've climbed up the staircase, which is what the A to D converter is doing, what do you do when you're at the top of the stairs and the signal is still getting bigger? Tough luck, buddy. You won't pick that up. Yeah, right. Some of these rigs will say overload, or I had a talking voltmeter, which I'll talk about a little bit later, that said "ouch" if you put too much. Yeah, yeah. One of the blind hams that I worked with, he had some special test equipment from the manufacturers, and one of them had "ouch" when he went over range. Yeah. So you got to watch out for that. You could make it too strong a signal. Also, what happens if you're sampling at a rate of, argument's sake, say a 1 nanosecond clock, which is basically a 1 gigahertz sampling rate? And yes, you could buy A to Ds today that'll do that. Empty your wallet, but you could do it. Okay. So what happens if you try to feed that 1.5 gigahertz or something faster? It's going to do what it can. And it goes into a mode that they call aliasing, in which it sort of like spurious responses out of your mixer. So what we have to do is put a filter in front of the analog to digital converter to minimize the signals that are over frequency. Okay. So it definitely has a limit. All right. And we have to understand what they are in these radios. All right. Next slide, please. Yeah. Wow. This is, it's been doing that all night. All right. Well, let's see. I wish I could. Oh, thank you. All right. Yeah. My apologies for the slowness here. Okay. Got to talk about quantizing. How do you divvy it up? Okay. So the simplest way to quantize a signal is to choose an amplitude value closest This says to the original analog amplitude, but I'm going to say no, that's not the thing you need to do. You need to make sure that your signal that you're going to quantize is set up so that it can quantize the highest value signal you can feed into it. Because if you feed into it an average value signal and say that's the range, the thing is going to get overloaded. So what do you do? So the answer is you have to design it so that it can get the entire range of the analog amplitude. Okay, so what this signal is doing here on the top, we have the green signal, which is the signal you want to quantize. And then we have the signal reconstructed, which is yellow. And then you see the difference between them is that little red line on the bottom that looks like noise. And that's just what it is. It's called quantized noise or quantization error. Okay. Now there's a lot of samples. It sort of looks like one of those arch bridges, when you're looking at this thing. But if you look down on the bottom, we see 2-bit resolution with 4 different levels of quantization compared to analog. Now that's good for a textbook example, but it's not very practical. There's just not enough signal levels. There's not enough stuff in there. And that's the kind of thing that people would do in a school's lab to show a kid how it works. Okay, here's one with 3 bits of resolution with 8 levels. That's pretty good. It's a little bit better. You can use that for some instruments, but it will make a crummy receiver, so we don't want to do that. So what happens? We're going to quantize the signal, which means we're going to set it up with a discrete value. And the difference between the input value and the quantized value is called quantized error. Think of the smallest possible step size, okay? And as you're going through it, you're never really sure of that smallest possible step size. And the good news is that if you have a good receiver with a decent A to D converter, that smallest possible step size is going to be quantizing noise because you have a signal to noise ratio, which is finite. And you're never really sure exactly where the signal is. And therefore, it doesn't matter as long as your step size is small enough to capture that information. Okay, so what do we have? We have some fixed point words. We have 8-bit sampling, which was very popular for a long time. It's still very useful for all kinds of things. We have 16-bit samples, which took over the audio world in the 1980s with the advent of CDs, compact discs. They will use 16-bit samples. They sampled at 44.1 kilohertz. And they there was a red book that's ISO 9660. And that worked out really well with very high quality. Unfortunately for the audio fanatics, I got to count myself as one of them. There was quite a few people that thought they could hear the difference between a digitized signal and the analog version of the same signal. So people who were true audio fanatics pressed the industry to go further, and the audio industry eventually settled on 24-bit, 24-bit, 32 bits of quantization running at 192 kilobits per second. And the good news is you can build such a chip. The bad news is there's no way you're going to get 32 bits of resolution. 32 bits of resolution implies that you could get a signal to noise ratio of 190 something dB. That isn't happening. Your thermal noise and the maximum voltage that you can actually work with that is much lower. Okay, and that's going to be something we have to talk about. So all these audio freaks, I think they're kidding themselves. Yeah, Brian. Yeah. Okay. So what's the closest your ear can hear? I'm going to start with what's the worst your ear will accept. I'll go the other way. Okay. And I'm going to talk to that because we have to talk about this concept called the effective number of bits. Okay. Which takes into account the signal to noise ratio and the ability of the receiving system to do something with the data. Okay. And I assure you that the finest devices that you can buy today exceed what any system is going to do. That's the good news. The bad news, you're going to empty your wallet. So, yeah, let's watch that out. Okay, next slide, please. Okay, let's talk about A to D. Let's talk about A to D characteristics. Okay, the first widespread use of A to D converters was in the telephone network. Not surprisingly, Bell Labs are the people that invented A to D converters that were practical to use, and they hold the patents on them. And a guy named Harry Nyquist, Dr. Harry Nyquist, described how that they would work. Okay, so the very first A to D converters were originally used in the public switch telephone network starting in the early 60s, and they used an 8 kilohertz sampling rate with 8 bits of resolution. Okay, they had filters in these devices that would cut off any frequency above about 3.3 kilohertz. That gave us a bit rate coming out of these things at 64 kilobits per second. Okay, that's pretty neat. Now, the step size that Bell Labs used for these things, for the public network, were not linear. Interestingly enough, the steps were not equal. So you had 8 bits, 2 to the 8th power is 256. So we had 256 steps, but the steps at a very high level amplitude were far apart. And then as they went to lower amplitudes, the steps got closer together. And that curve that they made was called a mu law. So mu law in the USA, the Europeans were working on the same thing, and they claimed they talked differently. So they came up with the exact same idea, but different step sizes. And they called that A law. Okay. So now we have the US networks and the European networks, which you couldn't plug into each other. Therefore, they needed different sets of equipment. And that was the whole point of having two curves, one curve for the USA for the Bell system, and the other curve to keep the Europeans from being overrun by the Bell system. So they required an A law, which the Bell system was patented out. They couldn't do it. Neither could Europe do the mu law. Hello. So over here in the United States, these things were called D4 channel banks, and they sold like hotcakes well into the 70s and 80s. And there's lots of things out there that use D4 channel banks in the public switch telephone network. So this was the first very widespread use of A to D converters. Okay. The next one is a completely different use. How many of you guys have digital voltmeters? Yeah, pretty much everyone, and Harbor Freight even gives them away. If you buy some stuff from them, you could get a free one, right? I know we've all done that, me included. Yeah, they work. Yeah. Mine's been out there a few years now too, and it comes in great for scout experiments because if the kids play with them, it's yeah. Anyway, what happens is that the most important characteristic that I'm trying to get to here is that an A to D converter actually forces you to measure your signal. That's something that your super heterodyne radio didn't do. I'm sorry, if you think you have an S meter and you think you were doing some kind of a repeatable measurement, good luck. Even an R390 was kind of dicey with the signal measurements. One of the things I did, and I was lucky enough to do, is I worked as a young guy. I worked in the RF laboratory of Fairchild Cameron Instrument over in Syosset. And yeah, they had an RF lab in there. I worked for Ed Pillar, who was the founder of Limart. Yeah, he stuck me in there. And we built measuring receivers back in 1972. And I was lucky enough to work on the BRT 30, 31, 35, and the FSR 50, FSR 1000, a whole bunch of receivers that would actually measure the signals. And they were operated by computers. At that time, it was a Hewlett Packard HP something or other, a 16-bit computer that you'd set with toggle switches. Yeah. And you would run paper tape through it to make it work. It was kind of interesting. So we did that. So in a digital voltmeter, speed wasn't all that important. What was more important than speed was accuracy. So how do you get accuracy in the thing? The A to D converter, of course. So 3.5 digit multimeters were very, very inexpensive. They used a relatively cheap A to D converter. They were as accurate as you could read on the display. If you wanted a more accurate one, you could pay a few more bucks and buy a 4.5 digit meter. And If you really needed something to be extremely accurate, and now I think I'm talking scientific experiments as opposed to engineering, Hewlett Packard would be happy to sell you a 6.5-digit meter. And I'm lucky enough to have one in my house. Thing works great. Okay, so what difference does this make? And the answer is we have resolution, okay, which is the smallest change that you can actually measure with this thing. Okay, so the resolution of the device with the digital output is the numerical resolution of the output, and it's made with precision with which the measurement is made, but they're not the same thing. Okay, resolution is how many digits can you read out on your display, but that doesn't necessarily mean it's accurate or precise. It just means that's how many resolutions you have. Okay, you know, you can have a certain amount of digits of resolution that don't mean anything if the signal is constantly varying or if it's buried in noise. So that doesn't really do you any good. So we have accuracy, which is how does it compare to some external standard, as opposed to resolution, which is how finely can you actually read the data. So there's some differences there. And we have this something called, this is important for our receivers, the effective number of bits. So it's a measure of the dynamic range of the A to D. So this is really looking at the input stage to it with the associated bits. What is the resolution of this thing? Okay. So if we have a 12-bit A to analog to digital converter, your effective number of bits isn't really going to be 12, even though it's 12 bits. Okay. And the reason why is that you have signals have noise. They're imperfect. They have noise and distortion. Okay. The distortion is from the step size on the A to D not being the same. Okay. Every time you go up a least significant bit, is that least significant bit the same value when you're measuring half a full scale input as opposed to measuring 1/10 of full scale input? That's going to make a difference. Okay. So we have a simple formula, which is the effective number of bits is equal to the signal plus noise plus distortion minus 1.76 divided by 6.02. And what this is telling you is that the number of bits on your output, on your analog to digital converter, is going to effectively tell you how many decibels can the thing measure. And the answer is very simple. Each additional bit on your output is going to give you 6 dB. So if you have an 8-bit A to D converter, that's good for 48 bits, 48 dB. Okay. So if you have an 8-bit thing, theoretically, you could get 48 dB out of it. Now, if you have a 16-bit A to D converter, 6 bits times 16 is going to give you 96 bits of effective resolution. And now at 16 bits, you're approaching some pretty hard limits. All right. But the industry has making 24 and 32-bit A to Ds. Okay. So at a 24-bit A to D, 24 bits times 6 dB per bit gives you a dynamic range of 180 dB. Yeah. Well, don't believe it. That's the technical number, but there are limits. At the lower limits, it's noise, which basically means is that your lower digits, the lowest numbers you can measure with it, don't mean very much because they're varying all the time because it's just crud. Okay. Then if you try to go high, the thing isn't going to measure 15,000 volts, which technically would be the upper end of the range. But guess what? That chip is fried if you come anywhere close to that value. So you could easily exceed the limits, the theoretical limits in the practical circuit. All right. So to keep that in mind, we just have the effective number of bits. And we have a simple formula to remember for that. And it also works as a quality measure for things like sample and hold amplifiers. And you have to include all that stuff in your signal chain calculation. So the effective number of bits of a chain of blocks, in other words, that's your receiver front end, is going to be less than the effective number of bits of the worst block. Okay. So what that really means is that the A to D is the key component in determining how well that receiver is going to work, but it's also dependent on the other things in front of it. All right, gain variations and so on. So for a hybrid circuit, using something behind that mixer, there's going to be more variables in that particular receiver, thus making it more difficult to measure stuff than it would be if that A to D converter was directly connected to a filter in your antenna. Okay. Okay. So we have the frequency band of a signal converter with the effective number of bits is still guaranteed. It's called the effective resolution bandwidth, and it's limited by the quantization errors. All right, so we have an aperture uncertainty. So an aperture in your A to D converter is when is it actually performing the quantization? Okay, so you're feeding in a clock to sample. Okay, so do you sample at the rising edge of that clock? Are you going to make your sample during the time when that clock is steady? Are you going to take your sample measurement when the clock is falling? And I've seen all three of these used, so it depends on your circuit manufacturer. So if you're into semiconductors and you want to look, Analog Devices Incorporated they have a great number of really good app notes that are very ham-friendly to take out and look to see how they work. You can also look at a company called Burr Brown, and they also make some very high-quality A to D converters. Okay, next slide, Marty. Yeah. Thank you. Okay. So bandwidth. This is something we're all concerned with. You know, how good is the bandwidth on our receivers? And we try to tailor them. Those of us that are CW operators, that would mean not me, but I think Ken is a really good one. So these guys, they want a really narrow bandwidth of 4 times the signaling rate. So if you're sending your code at 15 words a minute, you're going to want a bandwidth of about 4 times 15 words per minute. That's going to be about 60 hertz of bandwidth. That's awful difficult to achieve in any kind of an LC filter. But guess what? This is a computer, and you can recycle this thing and go through a fast Fourier transform, and you can actually get a digital filter that does a reasonable job at 60 hertz bandwidth. And it's perfect for these circuits, okay? So here we have some simple formulas, okay? So our sampling interval is X sub n, which is times your sampling period time, and n can be 1, 2, or 3. And the sampling rate is the inverse of the sampling frequency. And the requirement in an RF receiver is to sample the high frequency analog signal at a rate that captures all the information within the signal's bandwidth to ensure no critical information is lost during digitization. All right. So in an RF system, bandwidth refers to the range of frequencies over which the analog to digital converter can process signals. So it's determined by what we call the Nyquist frequency. And the Nyquist rate is twice the highest frequency that of the signal. So if you want to sample something that goes up to, say you want to do the 2-meter band, 144 to 148, let's round it up a little bit to 150. That means you have to sample at least 300 megasamples per second in order to pick up a 2-meter signal, properly. So your sampling rate has to be twice the highest frequency of the signal that you want to get. Okay. And what happens if it isn't? We get this fault in it that's called aliasing, which is if the input signal contains frequency components above the Nyquist frequency, they'll fold back and produce false and spurious responses. And that we don't want. So we have to have an input filter to keep that from happening. And that's called our aliasing filter, usually done in the RF stage. Marty, next step. It's coming. It's coming. Here we go. Okay, so what's our dynamic range in the A to D? I'll tell you, it's a lot more with the decent A to D than any analog radio that I know of. But the funny thing is, the input stage of the A to D converter is still analog. So if that single analog stage is the point at which the performance of the device is really going to be concerned with. That's really what's doing it. So we have the resolution, the number of bits. Is this an 8-bit, 12-bit, 16-bit, 32-bit converter, whatever? And what's the noise floor? And the noise floor is the traditional equation KTB, which is Boltzmann's constant times the temperature in absolute times your bandwidth. Okay, so we have to look at that. Then we have dither, which is actually forming noise that randomizes our quantization error. If we have a certain type of signal and we're feeding it into a fixed quantizer, that may produce an actual distortion depending upon which side of a bias curve you're looking at. So the whole point of dithering is to avoid the bias curve. For those of us that have ICOM 7300s, we have that function built in. ICOM lets us do that. It lets us add some dither to the signal to avoid the sampling method. Okay, then we have linearity, which is, are the step sizes exactly equal throughout the range? Okay, is the step size at a very large signal the same as the step size at a very small signal? That equality of the step sizes is known as linearity. So on the right, you see that we have a 6-bit signal, and you can see the noise, which is the quantization error, and then the signal rising above the noise in a little spectral display. The bottom one shows what happens if we have 8 bits, just 2 bits more, and you can see it's a much cleaner looking signal. Okay. By the way, the 8 bits at mu law is about the minimum quality necessary to get toll speech. Okay, so if you want to have good quality audio, you need at least 8 bits. For those of us looking at things like DMR and DVR for high frequency, we don't use a straight encoder. We actually use, we digitize our voice with the type of device that's called a vocoder. And the vocoder isn't actually our voice signals. It's instructions on how to reconstruct it. So when you're looking at your DMR radios, you're looking at radios that have vocoders in them. And try as it might, it's not, when it digitizes your speech, it's not actually you it's doing, you're providing an input into a device that's sampling it, and then it's providing a reconstruction of your voice at the other end. So it's not doing sampling the same way. Okay, so that's why DMR often sounds funny. Because it's not a direct conversion of your voice. It's going into a device that's going to tell it how to reconstruct the signal. Yeah, it's exactly the same as P25. It's the same algorithm. It's not the same as D-Star, and it's not the same as the Yaesu system fusion method either. So we have lots of differences there. Nor M17, which we heard about some months ago. Okay, next slide. Okay, spurious responses. Yes, A to Ds could give us spurs. Front-end overload, RF filters and shielding. If there's an extremely strong signal, it may peg your A to D converter so that it's actually trying to digitize a signal that's way beyond its range, and it's going to give you nothing but garbage on the output. So it's going to need some RF filters there. You may need some RF shielding. It's possible for your signal to mix with the clock. The clock is causing the A to D converter to sample. So what you want to do is to make sure that clock signal is going to be canceled out in the A to D circuitry itself. So many of them use a differential mode clock, which means you have A clock and then the B clock would be 180 degrees out of phase. When you mix them together, they subtract from each other, and that effectively cancels the clock signal on the output. But it lets the inside do clock work. Okay. We also can make an input clock trap filter so that any signals coming in at the clock frequency can be shorted out to ground before they hit the A to D. All right. And the nonlinearities, which is the step sizes not quite being equal. Semiconductor physics, the way you build the A to D chip itself has an effect. A lot of A to Ds are what you call laser trimmed. So after these things are made, the factory burns them in with the laser, and it's actually measuring each step size as it goes along. And the laser is burning the ladder networks inside the device chip itself. Okay, next slide. Okay, so we have some configuration trade-offs. The top one here is our heterodyne method, by which we have a somewhat lower cost A to D behind a mixer, and it's working at an IF frequency. Lower frequency, the A to D converter is cheaper. High performance, got optimum spurs, the dynamic range is reasonable. The challenge is it needs a lot of filters. All right, so there's a lot of hand tweaking in this thing. So it's not especially suited for mass production. These things are not handmade. They are mass produced. This is not acceptable for a phone. Okay, so instead, what we have today is a simple receive filter in front of the ADC that's clocked. You don't need a mixer. It's practical at L and S band. L and S bands are microwave terminology. L band is basically 1 to 2 gigs. S band is 2 to 4 gigs. And that's the range over which most of that stuff is working at today. But to do something at 4 gigs means you have to sample it at 8 gigs. And I assure you that's one expensive chip. That's a very high sampling rate today. And here you see some examples of what the signal outputs look like. On the top with the heterodyne effect, on the bottom with digital mode sampling. And this one has something which I'm not talking about, which is that the outputs are an I output and a Q output, which are 90 degrees in phase difference between them. I is in phase and the Q signal is quadrature phase. And this basically allows an IF stage, the numerical processing, to be a lot easier to get rid of signals. Okay, next slide, please. Okay, now a little brief bio about Harry Nyquist. He was an AT&T engineer. This was back in the days when Bell Labs was a premier research institution run by AT&T. And he was born in 1889. He was Swedish. He was an immigrant. And thank God we allowed immigrants like him into this country. Made a big difference. His work was to improve the way voice and video and data worked. He has 138 patents and a dozen technical articles. So that's a pretty good output from this guy. Try as I might, he was not a ham operator. I actually had ChatGPT going out and asking him what his call sign was. ChatGPT answered that it was W2CH. And so I went and looked up W2CH, and it wasn't Harry Nyquist. So don't tell artificial intelligence tools, don't ask them for a ham operator's license call, unless you also ask them to tell them where you got the info, because it didn't. Yeah. So the usual adage of, check your work is inherent in that. Okay. So he invented a fax machine. Okay. So the first fax images were 5-inch by 7-inch pictures sent from New York City to Cleveland. And it took each picture 7 minutes to go there, which is a hell of a lot faster than hand carrying it. And it sure as hell beat the Pony Express. Right. So he broke some new ground in solving communications and working. And he developed a mathematical explanation for thermal noise, now known as either Johnson noise or Nyquist noise, depending upon which book you read. And in 1924, he referred to a signal, an analog signal. Instead of calling it a signal, he called it information. And that was a key step to recognize that the signal itself had the material that you wanted to communicate with. So he suggested that signal and noise would determine the maximum speed of transmission of intelligence. Okay. And the source for it, interesting enough to us, was actually Morse code. He based most of his original work on the study of making A to D converters on Morse code. And that was his sampling point. Okay. So he discovered by looking at Morse code that the maximum speed of intelligence transmission is proportional to the logarithm of the number of symbols that needed to be represented. So when you think of all the different symbols for Morse code, then take the log of them, and that's how fast you can do. Okay, next slide. Okay, finally, we get his picture. So this is what the guy looked like. I always think that's important. Well, that is a cut and paste from a, any of it. His most significant work was a paper on certain topics in telegraph transmission theory, which if you're trying to look something up, that is about as vague can be. But it talked about how to improve transmission speed, and it talked about the bandwidth requirements and how to sample things so that you can convert them to digital and make it go faster. And again, in that paper, he again went back to Morse code as his sample point, something that's interesting here. And it was enormously influential to one of his engineers who was his protege, a guy named Claude Shannon, who's well known for basically, along with Norbert Wiener, for inventing information theory. And Claude Shannon is noted for how do you make transmission work better? Okay. So Nyquist's work influenced him. He had a lot of patents on this stuff. He invented the sampling theorem, and most of the technical informations in theory stemmed from the papers that this guy wrote. So he's enormously important. There was a Nyquist stability theorem. I don't know if any of you guys work with analog circuit design, but there's something called a Bode plot, which looks at phase versus yeah. This guy got into that. This is where it started from. Okay. After he retired from Bell Labs, he was a part-time consultant. He worked for the Department of Defense, and he received an awful lot of awards. He was the 4th recipient of the National Academy of Engineers Founders Medal, which is kind of like a really high-level prize back in those days. Sadly, he never saw the stuff that he started come to fruition. He died in 1976, just before CDs came out, just before cell phones came out, and to make digital audio recording and so on. So anyway, that is the end of my presentation, and thank you for putting up with me. Good. Thank you. Questions? I see there's some questions here.
George? George.
Yeah. Yes. Okay. Yeah. Hang on a second. Yeah.
WB2Y2K, KD2FIU.
FIU, take it.
George.
Go ahead, George.
Great presentation.
Thank you, George. Okay, let's get to your comment again here, which is that, analog
You're
we make,
welcome.
but as we become to digitize it, we can stretch the range of that analog and we can avoid some of the faults. For example, if one is listening to a phonograph record, okay, the phonograph record is not benign. It distorts our signal somewhat. The cutting length, as that cutting needle goes back and forth, is limited. Any dust and dirt will certainly make noises that you can hear. The turntable platter itself is going to wobble a little bit going up and down, and that's going to create this ugly sound called rumble, which if you have a really good subwoofer, I assure you I did, rumble will something you really don't want.
Island flutter.
Yeah, island flutter is variations in the speed, instantaneous speed. Tape decks do a lot of it. Cassettes were notorious for that.
Whoa.
Yeah.
Stretch.
There were 8 tracks. I mean, you guys had 8 tracks in your car once upon a time.
Never did.
A lot of people did, and they
I
were,
did.
they sometimes did bizarre things, especially in temperature extremes. And the good news is that this digital stuff is really doesn't seem to be sampled much. So, and I've heard people say that when they're listening to a CD, they like the record better.
Yeah.
Yours truly spent many years as a broadcast engineer. And I also was an audio
WLIR,
engineer. I was the chief engineer of WLIR.
Yeah.
I also worked for Telecare as a chief engineer of the television station. And if any of you guys watched Channel 21
Always.
during the 80s, yours truly brought it to you because I was the master control engineer responsible for putting that thing on the air.
The best
I had that
picture
job
in town.
from 1980 to 1987.
That was clear.
So
I can tell you all about all the little distortions and stuff that are in there. So, yeah, and to my ear, a CD, a well-recorded CD, sounds better than the typical phonograph record of the same material. So all these people that say they have golden ears have actually gotten used to defects in the sound.
Yes,
And it's not the pure sound that they would, that I think I would.
you can't press a record accurately enough, the equipment just isn't
You know,
there.
the comment is you can't press the record accurately enough, and then you mass produce it. And that's, actually, I've seen special transducers now for phonograph records in which they have photocells in them. And laser beam and a photocell, and that tracks the signal, so you don't even need to put a needle in the groove anymore.
ADC,
I did it.
remember ADC?
Yeah.
That record player?
And I gave the attendance.
The ADC was in a.
Because we
you could
transitioned
actually
so-
read the,
Smooth.
Yeah, there were all kinds of special.
yeah, I loved it.
So anyway, that's my talk, and thank you for putting up with it.
Thank you.
Ken's got a question. Sure, you seem very amplitude oriented as opposed to FM oriented. How do you? I guess when you're doing audio, how do you sample a level? You know, it might be one level at, let's say, 60 hertz and a different level at 2000 hertz.
The trick to audio sampling is to do it at a rate that's twice the highest frequency you pick up. Right, okay, so if it's audio, typically they say people could.
20 kilohertz. All right. My ears are not that good. They don't hear 20 kilohertz. Maybe not now. Now, on the other hand, my ears are exceptionally sensitive to very low frequency sounds. I've heard, I've heard 20 hertz to 20 kilohertz as being typical numbers, but honestly, I can hear notes much lower than 20 hertz. You could feel them too, but seriously, a large pipe organ is going to produce fundamentals of 16 hertz. That comes from a pipe that's 32 feet high. If you go to Atlantic City and you listen to Atlantic City for the Boardwalk Hall, and if you go to Philadelphia and you go to the Macy's department store downtown, there's a huge pipe organ in there that actually produces 8 hertz tones. It's almost equivalent to listening to an earthquake. Everything's kind of a rumbling around and, shuddering as opposed to a tone that you perceive. Ooh.
Then when you looked up, you saw instead of the pipes going like this, they were all.
Yeah, that would do it. That would do it. You're lucky you didn't, John. You're lucky you didn't get your hands cut off. Sister Mary Gertrude should have taken care of you. Yeah. No. Anyway, yeah. So a lot of us have much more experience with A to D converters in cell phones and in stereo systems as opposed to ham radios. Now with ham radios, I have an ICOM 7300, and I know that there's other people in this room that also have a 7300. And that's an example of a hybrid one in which there is a mixer. So there's an analog mixer in front of the A to D converter, and the A to D converter in the 7300 radio works at an IF of 24 kilohertz. Wow, which basically makes the converter a sound card, which means it can be very cheap and very effective. And the code that you put into it is called a fast Fourier transform. Bad news is I've run out of time, and the good news for me is that now I have to study fast Fourier transforms, which I am not expert at, but
Dongles.
What satellites?
Yeah, SDR
Get
is the top.
to come in.
You, maybe Section had a whole thing on SDRs, but her pitch on SDRs was, this is the commercial ones that are out there. So she went through the flex radios, and she went through,
Now I'm talking about the little dongles you can buy.
yeah,
He's got what? You got
$30.
you got the N.
Yeah.
And
like any of us that participated in
no Uno.
Project
Yes,
Green
the
Sky, the
SDR.
little tiles with the Raspberry Pis and the dongle attached to it. Yeah.
Yes.
That was an SDR.
doing?
Those are great.
Yeah, they work very well. I I used to have one, and I gave it back to Lou, so he could do some.
Yeah.
experiments.
So it's all in the memo field.
Yeah, I bought a Nano from Amazon.
What
I got two of
time
them.
does the,
Two in the package.
Nice.
I run Cube for, and hook it up to my antenna.
8:45. Well,
That looks like it.
okay. Any other,
Yeah, right.
any other questions here? Okay, that's it on my.
Yeah, I got SDR here too. You want me to crank it up?
There's no sort of, no sort of anything in these.
Does anyone want to give me dues tonight?
Alright, so we're gonna,
Richie's looking for money.
Anybody want to?
they're all gonna run out real fast. That's the quickest way to clear the room.
Yeah, me too. Don't have to worry about it.
Whoa! Now, you can get that back to me, kid.
Full of candy.
You can get that back.
Save this.
That's mine.
Yeah.